romanzi interi uscirra vehementi, in amardudine loquor vehementi, factus de metere azzinis elementi, similis poleo dec volundum venti, cum si teni proprium firo sapienti, supra petro ponere sede fundamenti, stultus ego comparo fluvio lamenti, sumeo de tramite nunca permanenti.
All right, so picking up where we left off, we were designing and implementing and testing an array-based list for initially for integers, but we're of course going to go ahead and make that more generic later on. Where we left it off was that we were testing a bunch of stuff, and I did look it up, and I actually figured it out right after the class. In JUnit, if you need to test whether or not something throws an exception, you specify what type of exception you are expecting, in this case a runtime exception. And then syntax is something we generally don't cover, but it's a lambda syntax. Basically, it's an inline anonymous function. If I were to write a function, like say foo, right, its name would be foo. But if I don't want a name to it because I just want to, hand it off, it's just one use, use it and then throw it away, then you don't provide a name. That's why it's anonymous, right? And it's called a lambda function. And then it maps to whatever code you put in between the curly brackets here. And so if that code list.getElement that is of 0, which is an empty list, that should throw a runtime exception because there's nothing in that list right there. You asked for something that doesn't exist. And so if we run this again, come on, run it. Right. I don't know why it's taking forever. There we go, finally, 3 out of 3, okay? All right, so back to our design here. Where we left off was, we already said that we already made the state. We are under the hood, we are storing everything in an array. Right? And then we're also keeping track of the size because the size of the array is its capacity. It's not the size of the list. We initially set that equal to 10, right? And then we added element at the end, right? By checking to see, is it already full? If so, we expand it. Right? Otherwise, we add it. And then we've got this other one that we have not done yet that we outlined. First of all, we need to, where we're adding it to an arbitrary index. All right, so first of all, we need to check that the index is valid. Now to do that, let's come back over here and understand what indices might be valid in the following case. All right, so for example, let me go ahead and create a list here, right, of say 10, 20, and 30. Right? No, those are indices 0, 1, and 2. Right? And so suppose that we want to insert or add 42. at index, say 0, or actually let's go ahead and say -1, right? 0, 1, 2, 3, 4, 5. Right? Now, which one of these are bad and which one of these are okay? Now, if it was negative, obviously that's going to be bad, right? So we don't want any negative values. But what about inserting it at index 0? What does that mean? We would end up inserting 42 right here. In other words, all of these things need to be shoved down, right, to make room for it. That one seems okay, right? So let's go ahead and mark that as green, right? That's a valid index. Likewise, if you wanted to insert it at 1 or 2, you would end up shoving 20 and 30 down, or you would end up shoving 30 down. So those two are perfectly fine, right? 1 and 2. What about 3 though? Right? Now here's 3, right? Should we be able to insert 42 right here? Seems reasonable to me, because that's just inserting it at the end of the list. In fact, that's what the first function that we wrote actually does. So this should be okay as well. Right? What about 4 though? Right, so here's 3 and here's 4. Should we be able to insert 42 here with a gap in between? I don't think so. So let's go ahead and say that that's not good, and of course anything beyond that is not good. Right, now what's the size of this list at this point? It's 3. So anything that is 0 up to and including the size is okay. Anything that is negative or that exceeds the size, is strictly greater than the size, is not okay. Some good whiteboarding. If the index is negative, less than 0, or the index is greater than, strictly greater than, this dot get size, right? Then we will throw a new runtime exception. Cannot add element at index, and then I'll just go ahead and concatenate that index. There we go. And of course, we would need to test that, right? But I've already shown you how to write those tests, so we're good, right? All right, now check to see if the size is it's full, basically, and we need to resize. Guess what? We already wrote code to do that, didn't we? So copy and paste. It checks and also it expands at the same time, and paste. There we go. Good idea to copy and paste. Don't repeat yourself, the DRY principle. What should I have done with that chunk of code that's responsible for expanding? Right? Should I have repeated it in 2 locations? Nope. Instead, what should we do? We should put it into a function, right? But should we make this public? Void expand, right? All right. I'm going to put that code right here. It's only going to expand it if it's necessary. So this function expands the underlying array by an additive factor of 10 if it is full. Otherwise, it doesn't do anything, right? If it's not full, then it doesn't end up expanding here. Right? Should we make this public? Should I just allow anybody from the outside world here over in my demo? Should I just go ahead and allow you to expand it? Foo.expand. Right? Should that be public? It doesn't seem like it to me. Why? Because it's a leaky abstraction. Right? We are leaking out. If we make this public, then that means that we're leaking out information to the world that there is this underlying array under the hood that needs to be expanded sometimes and maybe contracted other times. Right? That's a leaky abstraction, and we don't want that leaked out to the outside world. So what we're going to do is we do want this into one function, but we're going to make it private instead. Okay? That's good design. Right? All right, so up here we will replace that repeated code with this dot expand. This dot expand. And I'm going to go back to the other function that does the same thing where I copied the code from, and I'm going to change that as well, but I'm going to wait for that. I'll wait on that, okay? All right, now what we have to do is we have to do number 2. 10, 20, and 30, we want to insert 42 at index 1. That means that 20 and 30 need to be shifted down. Well, first of all, we should have enough room to shift things down because we've already expanded it. So if it was full before, we had 10 elements and 10 spots, right, then that means that it expanded to 20 elements. And so we have enough room to shift these guys down to make room for it. Right? How do we go about doing that, though? Right? For int, where should I start this? Basically what I want to do is, let's visualize it first, right? All right, move you over there. All right, so if I had, say, 10, 20, and 30, and let's make 40 there, right? There we go. So 0, 1, 2, and 3. And we want to insert 42 at index 1. In other words, we wanted to put it right here. That means that I should shift things down. So can I just simply copy 20 over to 30? What happens? What happened to 30? It's erased, right? So do I want to start from this end and move things down? No. Remember that it has been expanded, right? Even though that's the end of our list, that there is this gap here now, or this expanded elements that we can start moving things over. So if I move 40 over first, right? 40, that means that I now have room to move over 30. Now I can move over 30, right? Right? And now I can move over 20. And now I've got enough room for 42. So I shouldn't start on the lower end. Where should I start? At the very end. So help me write a for loop that does that. For int I equals, where's the last element? Remember that we have the size. If there are 5 elements in there, well, then it's at 0, 1, 2, 3, 4. So I will start it at size -1. Right? I is something something. I. Now, am I going to go up? I'm going to go down. So I minus minus. That much is pretty clear. But where is my stopping condition here? So I'm going to leave that as a question mark here. Now, what I'm going to do is I'm going to copy array sub I over to array sub I plus 1. Right? Remember, I'm moving them over to the right. Right? 3 gets copied over to 4. 2 gets copied over to 3. 1 gets copied over to 2. All right? So I'm going, how do I do that? Well, array sub I plus 1, right, is equal to array sub I. That's it. That's all. It's just copying it over. I don't need a temporary variable because I'm not swapping things, right? I don't need to erase the ith element because it'll be erased once I copy over the element next to it, etc. Now, where do I stop my I? Less than or equal to something, right? So what should it be? Well, come over here. I needed to copy 3 over to 4. I needed to copy 2 over to 3. I needed to copy 1 over to 2, right? And do I need to copy 0 over to 1? No. So I stop when I is less than the index that I'm doing now, right? So remember, it's going down, I minus minus. So while I is greater than or equal to, what is it, index? There we go. Right. So that will execute when it's it's equal to the index. It'll copy index over to index plus 1, and we're good. I'm pretty sure. Of course, we need to test it. Now we can go ahead and place x at that index, and that's going to be array sub index is equal to x. And finally, what do we need to do? Increase the size by 1 because we have added 1 element to the list. Right. Let's test that in an ad hoc manner here because we still don't have enough scaffolding here to test everything using the other functions. And what I mean by that is, let's go ahead and start out with, here we go. That we've got 10 elements in there, and let's go ahead and insert 42 at index 1, just like we did in my example. So foo.add element, and we'll insert 42 at index 1. And what I'm going to do is I'm going to rely on the debugger here to look at this. So let's go ahead and debug this, and it'll stop at that last, yes, I want to switch my perspective. It'll stop at that last line 14 there, done, and so we can take a look around here. All right, once it's up and running, come on, it takes forever. It's because I'm screen sharing like this. All right, let's go ahead and expand foo. And let's look at the actual array. And it is of size 11, by the way. Did it make it in there at index 1? Yep, looks like it to me. So let's go ahead and stop the debugger. Is that the only thing that you should test? You should always test extremal elements. For example, what happens when we insert it at index 0? Let's save that and let's run the debugger again. Where should it be? At the very front. And 10 through 100 should now be shifted over. Did it work? Yep, worked again. You should also test the other extremal elements, or the other extremal cases, I should say. Right? Inserting it at 0, inserting it at 1, those look fine. Inserting it somewhere in the middle, we'd want to test that too. But the other extremal is going to be inserting it at the end. Right? So for example, if I wanted at index 10, right? That's essentially, here, done. All right, let's run that again so that we can take a look at it. There we go. And is it at the end? 10 through 100, and then we've got 42 at the end. Right? So it looks like it works to me. Right? Again, this is ad hoc testing. You would want to formalize this in your unit tests if this were a real thing, right? If this were a real design. Let me go ahead and come back over here. All right. Before we continue, I want to ask you before we move on to another function. I want to ask you. There's a lot of repeated code here, right? There's an index checking, right? There is an expansion, right? There's shifting down that's necessary, and then finally we're placing it and increasing it by 1. Except for the shifting of things down, this function is exactly the same. We've got repeated code here. Oops, sorry, the first 3 lines. That could be a call to expand. But then these two things are repeated right here. Which one of these functions is more general? Which one of these functions is more flexible, more useful? I'd say the second one, because I can put it at an arbitrary index, meaning that I don't have to implement this function. I can implement it in terms of the other function. Right? This.add element x to what index would you be putting this at if you wanted to add it? Remember, the behavior of this is that it adds it to the end of the list. Size. Oh, this.size. Because if there are 5 elements in there, where do I want to put it? 0, 1, 2, 3, 4, 5. All right, great. Why is that better? Because now I've only got one point of failure here. If this function is wrong, then that other function is wrong. But if this function is right, then that other function is right. Because that function does nothing more than call this function over here. I've adhered to the DRY principle. Don't repeat yourself. If you can have a function in terms of another function, you do it. Because now I only have to test this one function right here. Okay? Now, am I testing, 2 more things before we move on to another function, is are we really testing that function out? Right? Are we doing a lot of rigorous testing here? And I'm going to show you this is a tool that you've had access to this entire time. But now that we've done some substantial unit testing, now I'm going to show it to you. Right? This is called a code coverage tool. So right next to the play button is this launch list tests. Right? And this is what's called a code coverage tool. Let me show you what happens here. I've only got 3 tests in there. Right? How much of my actual code is being tested? Right? Well, that will tell you. Right? So any parts that are green were tested by at least 1 unit test. So my constructor here, that got tested. Actually, that got tested 3 times. Right? That add element, that got tested. Right? So good. Right? Of course, it doesn't test comments because comments are ignored. But what was not tested? Right? This check was tested, but it ended up being false. And so we never ended up not throwing this exception. That was never tested. We never tested out of bounds for add element with the 2 arguments there. Not only that, but we also never tested the shifting of elements. Because in my tests, all I'm ever testing is adding 1 thing to the list and checking to see if it got in there, or adding 3 things to the list to check to see if they got in there. Right? So this code coverage tool will tell you, no, you need more tests here because you didn't actually test this case and you didn't actually test this code to see if it worked. Right? By the way, if you need to clean up and get rid of all the colors there, go ahead and hit the X buttons just like anything else, and it gets rid of them. So now let's go back and rectify that. Right? I'm going to add one more test here. At test, right? And this is public void test. I'll call it 3. You should come up with better names, right? But what I'm going to do here is I'm going to create a list, and I'm going to add 11 things to it, just to make sure that it's forcing it to expand, all right, and call that code to see if that works. So for int I equals 0, I is less than, say, 10, I plus plus, right? And list.add element, and we'll just add it to the end each time, I, right? Now that's only adding 10 things. That will not force it to test that expansion there, because that's our initial capacity. Only if I add one more thing to it, right? Now it'll end up testing that code. Right? And let's just go ahead and test to make sure that the last one got in there. Expected. The last element should be 10, right? It should be 10, oops, int expected, and then int actual is equal to list.getElement. And the last one should be at index 10, right? Right? And assert that expected is equal to actual. Of course, I probably should be testing a lot more, like that first element, that should be 0. The second element should be 1. The third element should be 2, et cetera, et cetera. Right? But I'm just going to go ahead and run this to see if it works. Remember, now I've got 4 tests, and so I see 4 out of 4, they all pass. What does my code coverage now look like? If I come back over here to the integer array list, after it gets done, 4 out of 4, there we go. Right, there we go. That never actually got tested because we're not shifting anything, we're only adding to the end. But guess what? Now the expand has been tested. That wasn't tested. I guess the expand was tested, but I guess I should have looked at it down here. This would have been yellow, and then this would have been red. That's what I should have been looking at. Right? Let's add one more test to make sure that shifting of stuff gets down. Right? Right? Testing is a never-ending process here. Because in fact, what happens when somebody reports a bug, right, then you've got a new test case, right, and that you need to reproduce the bug in order to debug it, and so you put that into a test case and make sure that you verify that the bug is there by, oh, the test case failed. Now we need to go and we need to fix our code until that test case works. Right? This one we should be adding it where then? Let's go ahead and add it in reverse order. There we go. So I'm always, or not get element, sorry, add element. We're always adding it to the beginning. And then what should be at the end now? Should be 0, right? Because we're adding it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, right? And let's go ahead and just go to the code coverage immediately here. And we're going to be testing that like 10 or 11 times. There we go. It all passes. And over here, now that shifting code, where is it? There we go. Now it's all green. It actually got tested because we were always inserting it at the beginning. Right? One more thing. Let me go ahead and get rid of all that. We're good. One more thing I want to do here is something that you don't generally do in unit tests. I mean, you can do this in a unit test. But what I want to do is I want to really put this through its rigors. Right? I don't want to go up to 10. Oh, sorry. Let's go ahead and go up to, let's insert 1 million things into it. There we go. Is that 1 million? Yep, that's 1 million. So I'm going to go ahead and add element, always at the end here. Right? And then we'll go ahead and ignore that. Right? There we go. So what I'm about to do here is kind of what's called a load test. What I'm going to do is this efficient? Can I insert 1 million things? How long does it take to insert 1 million things? Right? And let's go ahead and run it. This is just going to be a regular old run here. Now, it's probably going to take a little bit simply because everything is slow because I'm screencasting this. That's really slow. Come on. Let me go ahead and stop that. Let's kick this down to only, 10,000. And let's add some more Poor man's debugging here, starting, dot, dot, dot. There we go. All right, and let's go ahead and run that one more time. Make sure that's actually starting and done. Okay, there. That was way quicker, 10,000. All right, that was in a blink of an eye. What about 100,000? All right. Starting, 1, 2. All right, it was a little bit more noticeable, a little bit more, right? And so it took maybe 1 or 2 seconds there. I wasn't going 1,000, 2, 1,000. But this one will probably take, what, maybe 10, 20 seconds here for 1 million elements. Does anybody timed it? 1, 2, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000, 9, 1,000. I've got my timer up there. There's probably 15 seconds there. Come on. Don't make me a liar. It should only take about 20 seconds, 20 or 30 seconds. All right, it's intolerable. I'm impatient. I'm going to go ahead and kill it. And the way that we can improve this, remember I said it was kind of inefficient to only increase the size. Let's go down to expand. Right? It was kind of inefficient to only increase it by a size of 100. Let's go ahead and go with 1,000 there. Right? And let's see how much quicker it is now. And again, it's not going to be all that quick even now because I've got a million things open on my computer, but that was way quicker, right? All right, so we know that it's possible to get this done in like 2 seconds. Let me try something else though. What if I am inserting it at the beginning of the list every single time? Let's try this now. Now remember, it only took like 1 or 2 seconds there to insert 1 million things. How long should I wait? 10 seconds? Okay. All right. 1 million things. It's been more than 10 seconds now. How much longer should I wait? A minute? 10 minutes? Try decades. Right? And that I'm not even going to let it go anymore. Right? Try decades. Right? Literally, it will probably be years. Right? We'll get into the exact numbers later on. But why? What is so much worse about between always inserting it at the end versus always inserting it at the beginning? Right? Remember, this one went by with a blink of an eye, or at least 2 or 3 seconds or something like that, right? But if I insert it at the beginning, now it's going to take decades or years or decades to do that, right? We're going to have to understand that at some point, and we're going to come back to that when we look at algorithms and algorithm analysis. But otherwise, there's some load tests. I'm going to go ahead and kick this back down to 10 here, just so that we can continue developing this stuff. All right. Where are all my to-dos? What else needs to be done, right? If you look over here on the right, you'll see that any to-dos are highlighted in these little blue brackets here. So I can just click that and go immediately to it. Update element, right? So it replaces the element at the given index, x, returning the original value. Do I need to expand it or contract it at all? Nope. But I do need to do what at the very first up here? What is the first action I've been doing in any of these functions? Checking the index. If the index is negative, or the index is greater than or equal to this dot size, right, then I will throw a new runtime exception. Cannot replace element at index plus index. Right? Why did I go greater than or equal to? If there are 5 things in there, what are the legitimate elements that you can replace? 0 through 4. So if it's 5 or greater, then we throw an exception. Okay? Now what we can do is we can go ahead and reset it. So this array, dot array, so of index, we know that it's in bounds, right? And we can go ahead and set that equal to x. Ooh, return what? Remember, I'm going to return the original value. At this point on line 82, is the original value still there? We've overwritten it. So what should we have done first? Save it. Int result, let's call it, right? This dot array, so index. And then I can return the result. Do I need to increase the size? Nope, because we took something out, we put something in, the size stays the same. That one should be pretty easy to write a unit test for. Okay, I'll let you do that as an exercise. What about remove element? So this one we should whiteboard because this one is a little bit more complicated. Let's come over here and let's look at, okay, fine. Let's look at, say, 10, 20, 30, and 40, and 50. Oh, there we go. And suppose that we want to remove index equals to, say, 2. 0, 1, and 2, 3, and 4. In other words, we want to remove 30. Well, remember, we also wanted to return the value. So let's go ahead and put this into a temporary value right now. Temp is equal to 30. And we're eventually going to return that. Right? But what does it mean to remove it? Right? So, should I just take it out like that? Do we want to leave a gap there? Nope. So what am I going to do? I'm going to take 40 and move it down. Well, I don't want a gap there either, so I'm going to take 50 and move that down. Right? Once that's there, then I'm at the end of the list. It doesn't matter if I leave 50 here or not, because what I'm going to do is I'm going to decrement the size, and now the size is only 4. Right? And then 50 ends up being cut off anyway. So there's my outline. Right? First of all, outline this. What's the very first thing I should do? Bounds checking. Right? 2, save the value to return it. Right? And then eventually return it. 3, shift all elements down, that is to the left, to fix the gap. Right? And then finally 4, return the temp value. Actually, before we do that, what should we have done? 3.5 size minus, right? Because we're going to decrement the size. Right? All right, great. Bounds checking. In fact, at this point, I have this check here in several different locations. But that's okay. I mean, I don't want to put, I can put that into another function and I could reuse that function everywhere. But each time I throw something, I want it to throw a different message. Cannot replace that element, cannot insert that element, cannot retrieve that element. Those are different messages, and so you have a justification for repeating code in this case. Right? I'll go ahead and put the check there. Cannot remove element at that index. Right? It's a different message, so of course we need to have different code. Save it off. Int temp is equal to this dot array of index. Right? And then eventually we're going to return temp. Return temp. There we go. All right, and then size minus, we can go ahead and take care of that right now. Size minus, this dot size. Right. How do we shift elements down? Okay, to fix that gap. In this case, I do want to start at that index. For int I equals index. Right. I, some relation there, I plus. Right. Right. And what I'm going to do is I'm going to take the thing over here and copy it into the ith element. So this dot array sub I is equal to this dot array sub I plus 1. The one further over, right? I'm shifting them down. So I plus 1, I'm taking I plus 1 and I'm replacing I with it, okay? How far do I go? Right. Well, let's come over here and look at an example. Right? In this case, I copied over I is 2, I is 3, because we are copying over 50 over here, but then I stopped, right? So what was the size of the list before? It was 5. So I should stop 2 less than that, generally, okay? So what should it look like? I is less than this dot size minus 1. I'm going strictly less than. If I wanted to go less than or equal to, then I would do minus 2. Okay. And that looks like it should work. Again, let's do some ad hoc testing here. I'm going to go ahead and insert 10 elements in there, and then foo.remove element. Let's go ahead and remove, I don't know, the element at index 2. There we go. And int x is equal to, and let's make sure that we remove that element. So system.out.println x. All right. Let's just go ahead and run this. What should be the third element there that we just removed? Remember that we're inserting 10, 20, 30, 40, 50. So it should be 20, or 30, 10, 20, 30. All right. So it looks like we removed the right element, but again, that all went in a blink of an eye. I want to actually see if it shifted stuff down successfully. Right. So let's switch over to my debug mode here. And we've got 10, 20, 30 is now gone, and 40, 50, 60, 70, 80, 90, 100 have all been shifted down. 100 is still there, but that was the original 100. Remember that the size is now 9. Okay? So that looks like it works to me too. Cool. We have now achieved CRUD, right? We have achieved a way to create stuff, put stuff in, a way to take stuff out, a way to remove stuff, a way to replace stuff, right? My package editor over here, right? Now, of course, we've got a hell of a lot more testing to do here, but we also want some bells and whistles, right? These are just the basic things, right? This is CRUD, create, retrieve, update, and destroy. What else might we want in this implementation before we move on? This entire time, I've been relying on the debugger to display the elements, right? Maybe you actually want a way to print them out. So, how would we achieve that in our class here? Public void print this list out, right? Is that the correct method that we should be using? No. What should we be using? What should you have used, for example, in your projects? If you wanted to print out an invoice, right? What if you wanted to print out a service, right? Everything has a toString method that you should override. Right? String. All right. That means we're going to have to build a string out of this. String builder. This is how I would do it, at least. SB is equal to new string builder. All right. And then I'm going to iterate through each one of these and concatenate them and put them, put a nice comma in between them. So for int I equals 0, I is less than this dot size, I plus plus. Right? SB dot append, this dot array, sub I. There we go. And then SB dot append, a comma in between it with a space maybe to make it look nice, right? And then at the end, we'll go ahead and return sb.toString. Now over here, now I don't need to use that debugger anymore. What could I do? Well, once I've removed it, I could go ahead and print out the entire list by itself, foo. Okay. Let's run that again and see, do we get everything there? Yeah. Doesn't look very pretty right now. I mean, it looks all right, but I don't like that Oxford comma sitting at the end. Also, I want to know that this is a list. So let's print it out with square brackets there. Right? So sb.append. At the end, what we'll do is a square bracket. Oops, just a square bracket. And at the beginning, we'll add a square bracket, but an opening one. That'll make it look a little bit nicer. How do I get rid of that trailing comma, though? Go one less, right? And then sb.append, this dot array, where's the last element? This dot size, -1, right? And that's it. We don't want a trailing comma after that one. So let's go ahead and run this again and see if it looks nice and pretty. That looks nice. All right. You can modify this so that if you have a really long list, you could have line breaks in there so that you only ever print out, 10 numbers to a line or something. You can make it look as pretty as you want, right? But otherwise, now we've got a toString method, and I don't have to rely on the debugger anymore to look at it, right? Okay. What other kind of functionality would you want? We're not going to do it, but what other kind of functionality might you do? Secondary functionality, for example, right? What else would you want in your list? Right? For example, bulk, add, or remove methods. Right? So for example, add all, right? Or clear. I'll put these into code mode. There we go. Or remove all or whatever, right? So if you had an entire other list and you wanted to combine two lists, right? You could append this list to that other list. What else might be useful? Maybe a find element, right? So you've got a list and you want to find 42, right? Find element or contains element, right? Does 42 exist in there? Yes or no, true or false? Okay, 42 is in there. Where is it? It's at index 5, right? Maybe you'd want a copy constructor, right? Where it allows you to create a deep copy of your list, right? Maybe other methods that you can add to the beginning or end. We already did that one of the list, right? Add functionality to shrink the list if it is too big. And by too big, I mean, you increased your capacity, so now it can hold 1 million elements, but you're only storing 5 in there. Maybe you should take that as the opportunity to shrink it down or something if it gets too small, right? Maybe a sublist, right? That is I to j, right? A function, or method I should say, method to return a new list that is a sublist from I to j, inclusive, exclusive, right? Okay, et cetera, right? Do we want to do one of these before we leave? All right, choose one. Okay, shrink the list. All right. So instead of doing it fully, what I'll do is I'll do another function, not called expand, but what's the opposite of expand? Unexpand. All right, void de-expand, unexpand, contract. I like that. All right, so what's your criteria? It can no longer be that it's full or that it's empty either, right? You don't want 1 million elements and you've still got 5 here. Only when you delete those 5, now you contract it down to nothing or something, right? So what's your criteria going to be? If too much space is wasted, basically, ... Right? Then we will contract. So what about, this is the hard part, right? Well, how about, we expanded it by 1,000, right? So if there are 1,000 or more unused spaces, let's make that our criteria, right? So in other words, if the capacity is greater than or equal to the size plus 1,000, right? Then we'll contract it, okay? Well, what is my capacity? This dot array dot length, right? What's my size? This dot get size, right? And then what's 1,000? Well, it's just 1,000. And by the way, I'm using 1,000 in 2 places. Remember where those are called from CS1? Magic numbers. Where the hell did you pull out 1,000 there, right? I just chose it, right? It came out by magic, right? What we should be doing is we should be taking that and putting it into a variable, right? So let's do that before as part of this. I'm going to make it into a private static final int. And what should we call this thing? Is equal to 1,000, right? So we're expanding it by 1,000. We're contracting it by 1,000. I don't know, scale? Okay, I like that. Again, remember, there are only two difficult things in computer science, and one of them is naming things. And so now I'm going to go ahead and come back down here and replace all my instances of 1,000 with, well, fine, 1,000. There we go. With scale and scale. There. Now, is that the right math? So if this size plus 1,000 is greater than or equal to the length, that sounds right to me. Right? Then let's go ahead and contract it. Well, how do we contract it? I'm going to steal the same code up here, but minus. Right? It expanded it by 1,000. We're now going to contract it by 1,000. Right? And now it expands and contracts and expands and contracts. Now, where would you actually call this? Well, we would call it in the same places where, well, we would call it here, right? When we remove an element, then the size is going down. After we've removed it, before we return the value, we can, what did I call it? Contract. I could pull that up. This dot contract. There we go. All right. And so that'll make a check. Did we contract it? Should we be contracting it? No, we've only got, we'll have 20 unused spaces. We shouldn't contract it yet, right? You don't want to contract every single one because then it gets extremely slow, right? As we already saw, what happens when you insert it at the beginning all the time. All right. I will leave the rest of them to you. But before we do that, and we're going to have a whole week off here, I'll ask you, what is this design good for? What's the only thing that this implementation and design is good for? Integers. I want to store doubles now. What should I do? Copy paste the whole thing and change every integer to a double? Now I want to store strings because I want to store usernames or passwords or something like that, right? Copy everything, change all the integers to strings. Now I want to hold invoices. Copy everything, change all the integers to invoices. Should I be doing that each and every single time? Nope. Instead, what are we going to do? We are going to parameterize it like you did in lab 5, or 5 or 6. I forget which one it is. 6, I think it was. Right? We're going to parameterize it so it doesn't just take integers or doubles or strings or invoices. It takes anything, right? And then basically we've repeated the design and implementation of the array list in the Java collections library. But that's where we'll pick it up on Monday after the break. All right? Don't expect design documents to be graded until after the break because, again, LAs, they're on break too. Right? So have a good break.